Hello friends, welcome back to my YouTube channel. Welcome to my discussion on distillation. In this video, I'll be discussing a numerical that is based on calculation of relative volatility. In my previous video, I had discussed one such numerical. So today, I'll be discussing a other type of numerical that is based on calculation of relative volatility. I hope you are watching my videos on distillation. I'm giving links to my earlier videos in the description section. So this is part 8 of my discussion on distillation. Please go and watch my earlier parts on distillation. I'm giving links to those videos in the description section. So this is numerical 2 that is based on the concept of relative volatility. So let us understand. First, let us look at the statement. The statement goes like this. A liquid solution of methanol, which is being denoted by A, and water denoted by B, it can be assumed to be ideal for practical purposes. The vapor pressure relationship for each component is given by the following equation. You have Antoine equations. For component A, this is given as log to the base 10 of PA naught is equal to 8.07247 minus 1574.99 divided by T plus 238.86. So this is Antoine equation for methanol, which gives its vapor pressure. PA naught is vapor pressure of methanol. Then for water, the Antoine equation is log to the base 10 of PB naught is equal to 8.07131 minus 1730.63 divided by 233.426 plus T. Okay. So while using this equation, vapor pressures, that is PA naught and PB naught, they will be in mm of Hg, whereas temperature to be used in this equation has to be in degrees Celsius. So with this data, we will calculate the average relative volatility, first task. Then we will generate the VLE data at 1 atmosphere, and then finally we'll be plotting the distribution curve, distribution diagram, and also we will be plotting the boiling point diagram. So let us understand this. Let us know how to solve this. So what is given to us? You have methanol and water solution, and it is said that they are forming an ideal solution. So if they are forming an ideal solution, we can use the concepts that are applicable for ideal solutions. Then equations for vapor pressures of the two components, PA naught and PB naught, they are given to us. While using this equation, you have to use temperature in degrees Celsius, whereas PA naught and PB naught, the vapor pressures that will be obtained by using those equations, it will be in of Hg. And then we have to calculate average relative volatility, that is alpha AB average. Then generate the vapor liquid equilibrium data at 1 atmosphere, plot the distribution curve, and then plot the boiling point curve. Okay, so let us move ahead. What are the steps that are to be followed in this? Let us understand. First, we will be calculating boiling points of A and B, that's methanol and water, at 1 atmosphere, and let us denote those boiling points by TA and TB. Then we are going to select, after calculating the boiling points, next step will be we are going to select various temperatures between the boiling points, boiling point of pure methanol and boiling point of pure water. Then after that, the third step will be calculation of PA naught, vapor pressure of methanol, vapor pressure of the vapor pressure of water, and then the relative volatility of methanol relative to water at each of the selected temperature. So whatever temperatures we are going to select in step number 2, at each of that temperature we are going to calculate alpha AB. Okay. Then fourth step will be, after getting different values of alpha AB at various temperatures, you just have to get the average of alpha AB. So that will be one task. And then after getting alpha AB average, we will be generating the VLE data. VLE data is nothing but XY data, where X is mole fraction of A, which is the more volatile component, in this case methanol. Mole fraction of methanol in liquid and mole fractions of methanol in vapor phase. So that XY data, which we are going to calculate at equilibrium, that is called VLE, vapor liquid equilibrium data. So we are going to generate that. Then after getting that data, we will be using that data to plot the distribution diagram. Distribution diagram is, we will be plotting on x-axis. We are going to plot mole fraction of methanol, that is more volatile component in liquid, and on y-axis we are going to plot mole fraction of methanol in vapor, and the resulting curve that we will be getting, it is called the distribution curve, distribution diagram. Okay. Then we are also going to plot the boiling point diagram. What is boiling point diagram? So in step number 2, we will be selecting various temperatures between the boiling points. So, and in this step we are going to generate VLE data, that is XY data. So that data will be plotted in this way to get the boiling point diagram. So on y-axis we will be plotting temperature, and on x-axis we will be plotting both x and y, that is mole fraction of methanol in liquid and mole fraction of methanol in vapor. So you'll be getting two curves. One is t versus x curve and the other one is t versus y curve. So this is t versus x curve, t versus x curve, and this is t versus y curve, t versus y curve. So this diagram, we call this as the boiling point diagram, where the diagram will be giving us boiling point of the mixture at various compositions. Okay, so this diagram we are going to plot using temperature and XY data. Okay, so let us move ahead. First step, as we had listed, is boiling point of V, and that we will be calculating at 1 atmosphere, and 1 atmosphere is 760 mm of Hg. The fact is, at the boiling point, vapor pressure is equal to the total pressure. So for any liquid, the boiling point, at boiling point, its vapor pressure becomes equal to the total pressure. So for A, if you take example of A, methanol, so at boiling point of methanol at T is equal to TA, vapor pressure of it, methanol, a PA naught will be equal to P. And at T is equal to TB, that is at boiling point of B, vapor pressure of B will be equal to total pressure. ठीक है. So for component A we have Antoine equation log to the base 10 of P naught is equal to 8.07247 minus 1574.99 divided by 238.86 plus T. So what basically we are going to do, the vapor pressure will be equal to total pressure, and if that is the case, this temperature will be equal to the boiling point. Okay, so I have replaced Pa naught with P, which is known to us 760 mm of Hg, and T temperature is replaced with Ta. Okay, so after solving this, we know value of P. After solving this, you'll be getting value of Ta, which is boiling point of methanol at 1 atmosphere. Okay, so in the next step, I have used P is equal to 760. And then further simplification gives 2.881 is equal to 8.07247 minus 1574.99 divided by 238.86 plus Ta. So if we simplify it further, we will be having 1574.99 divided by 238.86 plus Ta is equal to 8.07247 minus 2881. Again, the next step will give us this equation 1574.99 divided by 238.86 plus Ta. This difference is 5.19. So in the next step, I will bring this term to this side and this term to this side. So it will be 1574.99 divided by 5.19 is equal to 238.86 plus Ta. Then next step you get 303. This division is 303.47 is equal to 238.86 plus Ta. And finally, after solving it, we will be getting Ta, that is boiling point of methanol at 760 mm of Hg is 64.61 degree Celsius. Okay, so over here we have used Antoine equation for methanol to get its boiling point at 1 atmospheric pressure, which is 760 mm of Hg. Okay. Similarly, we will be calculating it for component B. For component B, the Antoine equation is log to the base 10 Pb naught is equal to 8.07131 minus 1730.63 divided by 233.426 plus T. Now in the next step, what we will be doing, we will be replacing Pb naught with total pressure and temperature with the boiling point to get the value of the boiling point. So in the next step, Pb naught is replaced with P and T is replaced with Tb. Okay, so we just have to solve it, simplify it. So P is 760 and we are going to get Ta. So in the next step, we have log to the base 10 is log to the base 10 of 760 is 2.881. And now we are going to get Tb. In the next step, after rearranging the equation, you have 1730.63 divided by 233.426 plus Tb is equal to 8.07131 minus 2.881. In the next step, you get the difference. So this is 1730.63 divided by 233.426 plus Tb, that is equal to 5.19, and which further gives 1730.63 divided by 5.19 is equal to 233.426 plus Tb. So if you simplify it, and then you'll be getting Tb, which is boiling point of water at 100 degree at 1 atmosphere, and we know it is 100 degrees Celsius. So over here we get Tb as 100 plus 100.024 degrees Celsius. That is, it is almost 100 degrees Celsius. Okay, so we got boiling points of the two components at 1 atmosphere. Now that ends our step number 1. Second step was we were going to select various temperatures between the two boiling points. So second step is selection of various temperatures between TA and TB. So I have selected these temperatures. So starting with boiling point of A, that is methanol, which is 64.61, and the next temperature that I have selected is 70. It is random selection. You can select other temperatures. There is no problem in it. So 70, 72, 74, 76, 78, 80, 82, 84, and so and so 84, 86, 88, 90, 92, 94, 96, 98, and 100. So I have selected these temperatures. Then at each of these temperatures I will be calculating these three parameters. One is I will be calculating vapor pressure of A, and then I will be calculating vapor pressure of B, and the relative volatility. Okay, so alpha PA naught vapor pressure of A, PB naught vapor pressure of B, and alpha AB is relative volatility, that is volatility of methanol relative to that of B. Okay, uh, these three the three parameters PA naught, PB naught, and alpha AB, they will be calculated at each of the temperature that we have selected. And to understand the calculations, I have done calculations for one temperature, that is first temperature 64.61. So first we'll calculate PA naught. So for that I'll be using the Antoine equation that is given to us. Log to the base 10 PA naught is equal to 8.07247 minus 1574.99 divided by 238.86 plus T. Okay. So now I'll be what will be the task? We will use T as 64.61. So I have done that and simplified it. So I get log to the base 10 of PA naught is equal to 2.881. So if you solve this part of the equation, you get it as 2.881, which gives us PA naught is equal to 10 to the power 2.881. That gives us PA naught as 759.69 mm of Hg, which is almost 760 mm of Hg. The vapor pressure of methanol, because T the 64.61 it is its boiling point at 1 atmosphere. So naturally, if you use boiling point in Antoine equation, the vapor pressure that will be getting, it will be equal to atmospheric pressure. 759.69 is almost 760 mm of Hg. Okay. Then similarly, we will be calculating the vapor pressure for PV naught, vapor pressure of B, that is PV naught. So for that we will be using Antoine equation for B, which is log to the base 10 of PB naught is equal to 8.07131 minus 1730.63 divided by 233.426 plus T. So next task will be, we will just use T as 64.61 degrees Celsius. So if I do that, I will be getting this equation. So I have replaced T with 64.61, and then that gives me log to the base 10 of PB naught is equal to 2.26, which gives PB naught is equal to 10 to the power 2.26, which gives PB naught as 183.87 mm of Hg. Okay, so that means vapor pressure of water at 64.61 degrees Celsius is 182.87 mm of Hg. Okay. So we have calculated PA naught. Now we calculate PB naught. Now the third thing. Okay. Now in this next step is we will be finding out alpha AB. So alpha AB will be calculated by using this equation. Alpha AB is equal to PA naught upon PB naught. That is the ratio of vapor pressures of the two components. So this equation is valid if the solution is ideal, and in the beginning we have assumed the solution to be ideal. We calculated PA naught, that is 759.69 mm of Hg. Then we calculated PB naught, it is 183.87 mm of Hg. So you just have to use those two values to get alpha AB. Alpha AB, it comes out to be 4.13. Okay. So at the temperature of 64.61 degrees Celsius, we have calculated PA naught, we have calculated PB naught, and now we have calculated alpha AB. Okay. So this is to be done for the remaining temperatures. For all the temperatures, for all other temperatures that we have selected, we will be calculating these three parameters: PA naught, PB naught, and then alpha AB. Okay, so after getting PA naught, PB naught, and alpha AB at 64.61 degrees Celsius, for other temperatures, I have then followed the same steps to get those three parameters: PA naught, PB naught, and alpha AB. So PA naught at various temperatures, you have these values. PB naught at various temperatures, you have these values. Okay, so you just have to follow the same steps which I have done for first temperature 64.61 degrees Celsius. Okay. After getting various values of alpha AB at these temperatures, you simply have to take arithmetic average of these values to get alpha AB average. So alpha AB average comes out to be 3.77. Okay. Next step will be so first task is completed, calculation of alpha AB average. Second task is we have to generate VLE data. VLE data, as I discussed earlier, these are various values of X, that is mole fraction of A in liquid, and Y, that is mole fraction of A in vapor. So for each you can say set, we will be getting X value. So there will be different X values, and similarly there will be different Y values. So let us understand how it is done. So we know for ideal case where you have ideal liquid solution, and then the resulting vapor mixture is also ideal, and when they are in equilibrium with each other, you can apply Raoult's law. Okay, so using that concept, you get P, the total pressure, as PA naught into X plus PB naught into 1 minus X. Okay, so here X is mole fraction of A in the liquid, I have said this, and then this A is the more volatile component, which is methanol. Methanol is the more volatile component. Why it is more volatile component? Because its boiling point is less at any pressure, or its vapor pressure is greater at any temperature. So you know that concept. Okay. So if you simplify this equation, we will have P is equal to PA naught into X plus PB naught minus PB naught into X. I have simplified over here. Okay. So then after rearranging it, I get P minus PB naught is equal to PA naught minus PB naught into X. So out of this two, X is taken common, and then PB naught is brought on this side. So that gives us X as P minus PB naught divided by PA naught minus PB naught. Then by using Raoult's law, because Raoult's law is applicable to vapor liquid equilibrium when they are behaving ideally and when they are in equilibrium with each other. So you have Y into P, that is mole fraction in vapor phase into total pressure, is equal to vapor pressure of pure A into its mole fraction in liquid. So Y is mole fraction of A in the vapor phase. Okay, so we'll be using this equation for getting X and this equation for getting Y. Okay, so let us understand that. So again we have just got an equation for X, which is P minus PB naught upon PA naught minus PB naught, y into p is equal to p a naught into x as per Raoult's law. That gives us y as p a naught upon p into x. Now let us get values of x and y at first temperature in the list, that is 64.61 degrees Celsius. So at 64.61 degrees Celsius, Pa naught is 6, the total pressure is 760 mm of Hg. Pa naught, sorry, Pb naught is 183.88, so I have used that, divided by Pa naught. Pa naught is 759.69, so 75.69 minus Pb naught. Pb naught is 183.88. So if you simplify it, if you solve it, you'll get x as 1. Then we will use this equation to get y. So y is equal to Pa naught. Pa naught is 759.69 divided by P, total pressure is 760, into x that we got earlier, it is 1. So it is 759.69 divided by 760 into 1, that gives us y as 1. That means at the first temperature, x is 1, y is 1. And how we have got those two values, I have explained over here. Okay, so similar calculations will be applicable for remaining entries, for remaining temperatures. So in that way, you will be getting x and y for each of this temperature, and all those x and y values will be the xy data, which is nothing but vapor liquid equilibrium data, the data of compositions of vapor and liquid when they are in equilibrium with each other. Okay, so similar calculations are done at other temperatures. Okay, so I'm showing you, after using all those steps that I just told you, I get various values of x, then I get various values of y. Now in the now our next task is, that means the task of generating VLE data is completed. Now next task is we have to plot those two diagrams. One is the distribution diagram and the other one is boiling point diagram. So what we will do, I have done, I'll be plotting the distribution, boiling point diagram first. So for that, x and y, that is mole fraction of A in liquid and vapor phases, all those values, they will be plotted on x-axis, whereas temperatures will be plotted on y-axis. Okay, so xy, that is mole fractions in liquid and vapor phases, we are going to plot on x-axis, and various temperatures we are going to plot on y-axis. So if you plot the data that was generated previously, you'll be getting the boiling point diagram. So the blue curve is plot of temperature versus x. This curve, it is a plot of temperature versus x, and orange curve is a plot of temperature versus y. Temperature versus y. Okay. Why it is called boiling point? Because at each, let us say at by composition of 0.4, this will be, the boiling will start at this temperature, say 80 degrees Celsius, and then it will move on, and the boiling will be completed at this temperature. Okay. So you get boiling temperatures for methanol water solution at various compositions. That's why this diagram is called the boiling point diagram. Okay. So plotting of boiling point diagram, it is over. Now we are left with plotting of the distribution diagram. So for that, x, that is mole fraction of methanol in the liquid solution, it will be plotted on x-axis, and mole fraction of methanol in the vapor phase, it will be plotted on y-axis. Okay, so all x values we are going to plot on x-axis, and all y values we are going to plot on the y-axis. Okay, so if you plot the data, you'll be getting a curve like this. You'll be getting a curve like this. And for reference, we can draw a diagonal line. Okay, so the plot says that you can see this, the blue line, which is the desired plot, the distribution curve, and the diagram is distribution diagram. Now you can see it is lying above the diagonal line, which suggests that at every for every, you can say, point, composition or mole fraction of methanol in vapor phase is greater than in the liquid phase, and this conveys the fact that A is more volatile component. A being more volatile component, it is predominant component in the vapor phase, or vapor phase is rich in more volatile component. The fact that distribution diagram lies above the diagonal line tells you that vapor phase is rich in more volatile component. Okay, so that ends our discussion on this particular numerical, where we have learned, if you know the Antoine equations for the components, you can get how to get the relative volatility, then how to plot the distribution diagram, then and how to plot the boiling point diagram. Okay, so with this I end my discussion for on this particular numerical. I hope you have understood the concepts. If there are any doubts, please mention those doubts in the comment section. Do subscribe to my YouTube channel. Thanks for watching. Do subscribe to my YouTube channel. Tell your friends to subscribe to my channel. Hit the bell icon so that you'll get notified as soon as I upload any new video. And if you have liked it, you please like my videos. Thanks for watching this video. Have a nice day. Bye bye.